Good morning, everybody. Welcome to the second plenary talk of the day. Today, I have the pleasure to introduce Professor Joerg Bruedern from the University of Göttingen in Germany. Professor Bruedern is a prestigious mathematician, a well-known number theorist, a world authority on the circle methods, and I have the privilege of co-authoring 2 papers with Bruedern. And besides his excellence in mathematics, one characteristic that have made an impression in me is his ability of writing mathematics with style and elegance. This has made me aware of the importance of presenting one's idea in the best way possible, and why not with elegance and style. The title of his talk today is Linear Algebra in Powers, the Power of Linear Algebra. Thanks, Joerg, for accepting our invitation.
Good morning, Brasilia. It's a great pleasure to be with you. Many thanks, Hema, for your kind words. And I would love to be in Brasilia right now and give a Blackboard talk. So let me try how close I can get to that. It's always a bit strange to speak to a camera. So what is linear algebra in powers? Everybody knows how to solve linear equations. If you're given a system of linear equations, when we proceed like Gauss did, we do row operations, and then we can see all the solutions in one go. No problem at all. But what happens if I just change the problem a little bit and only allow you to use a certain fixed power, the div powers in my notation? So I've written down for you a system of linear equations in the standard matrix notation. And instead of just having the linear variables x1, x2, and xs, and so on, I just look at x1 to the d, x2 to the d, and so on. You can ask questions like solubility of equations like this over any field, of course, but I'm a number theorist and I'm mainly interested in the rational numbers. Since we are only looking at homogeneous equations today, it doesn't really matter whether we look at rational coefficients, we can just clear denominators. And similarly, we can just forget about solutions in rational numbers. It's the same question to just ask for integer solutions. Of course, you will tell me there is an integer solution quite easily. We can just take all the x's equal to 0. And for me, that is not a solution because I'm interested in a projective point on the variety defined by the equations that we see. I will sometimes just say a non-trivial solution if I mean that x is not the 0 vector. And now there are natural questions. Are there any solutions over the integers? And if yes, how many? And if there are really many of these, can I make some statements about the distribution of these solutions? And if no, then, well, do we understand why there is no solution? There could be many reasons, and maybe we learned something from the reason. So one simple reason is if a degree is even, and you just have one of these equations, then this is like 4 quadratic forms. It could be a definite form, and then there are no solutions, and we know why. Just because there is something like a sign. And then there is a final question. If someone writes down such a system, can we decide in a finite time whether there is a solution or not? So let me look at the simplest case, which is not really linear. That's the quadratic equations. And I just take one equation to start with. Well, just one variable is boring, but for 2 variables, we can assume that a1 and a2 are non-zero, because if a1 is 0, then we can just take x1 any number and have a solution by taking x2 equal to 0. That's uninteresting. But if A1 and A2 are non-zero, then if there is a non-trivial solution, when x1 and x2 are both non-zero, so I can just divide, and we see that we want to know whether minus the fraction of the two coefficients A2 over A1, and minus that should be a square in the rational numbers. Well, that's easy to solve by unique factorization. And if we assume we know the factorization of A1 and A2, we can write down the solution x1 and x2. So it's easy to decide that. With three variables, we're in a situation where we see one of the most beautiful theorems of elementary number theory, known as Legendre's theorem. Well, one can do a little bit of arithmetic if I'm given three coefficients, and there is a square in these numbers when I can absorb them into the variables, and I can therefore assume, after some modest thinking, to a situation where the product of all the three coefficients is square free, so no prime is there where the square of that prime divides that product. And if I'm now asking whether this equation has a non-trivial solution, unfortunately I forgot to write that down, and the answer is, this happens if and only if the negative of a product of two coefficients is a square modulo of a third coefficient. So that gives me three conditions. And it's an if and only if statement. So we're very lucky. We can decide whether a given number here is a square modulo A3 by just checking. So we get a condition that tells me in finite time whether this thing has a solution. And there is an easy geometric argument that tells you if you found one solution, then you can determine all others. There's a parametric way of doing this, so we really understand all the solutions of this ternary equation in squares. You will never have such perfect answers in any other case that I will be discussing today. Legendre's theorem is just a compact and elementary description of what in a modern version is the Hasse-Minkowski theorem, and that holds for any value of S. So we're given a diagonal quadratic equation, and the statement is there is a solution of this in integers, non-trivial of course, if and only if there are solutions in all completions of irrational numbers. So if you're not a number theorist, maybe this is not so familiar, but everybody knows that one can complete the rational numbers to the real numbers, and in the same way, you can use a prime to construct a different completion known as the p-adic numbers. And these are just generalizations or an easy way of thinking about congruences. So, and it's an if and only if statement. It looks strange to us, and one might believe that this doesn't help the decidability problem, but it does. Well, at first sight, it translates one question into infinitely many. I have to check all the completions. But checking whether a quadratic equation has a non-trivial 0 over R just means checking the signs of A1 up to AS. We should simply avoid a definite situation. And over the p-adic numbers also, the problem is essentially trivial if p is an odd prime, and it does not divide any of the coefficients. If that's the case, then even in the ternary case, you can already see almost with a naked eye that there is a p-adic solution. So there are only finitely many primes that actually matter here on the right-hand side. And the question is now, are statements true of this type, to which I will refer as the Hasse principle, for equations of higher degree? Well, let us see whether this is realistic by looking at the cubic case and just one single equation. Unfortunately, this Hasse principle that I just described does not hold for cubic equations in 3 or 4 variables. And I've written down for you The oldest example known due to Zellmer in 1950, which is easy to remember. It has coefficients 3, 4, and 5. And it is such that there is no integer solution other than the trivial one. But in all completions, there are solutions. So the Hasse principle is false. There is also an example in 4 variables. And the coefficients here are 5, 9, 10, and 12. And it's not a surprise to the expert to see that any prime that divides one of the coefficients hits another one. So you have a 3 here and a 3 here, and you have a 2 here and a 2 here, and you have a 5 here and a 5 here. So this particular example for equations in 4 variables is due to Kasselzinger in 1966. So it took quite a while. And nobody's ever found an example in 5 variables. The rumor goes, but this should be that the reason for this should be that the Hasse principle is true from 5 variables onwards for such equations, but I'm not willing to stretch out my neck and call that a conjecture. But there are positive results for equations of this type, and remember, I will always write R for the number of equations, D for the degree, and S for the number of variables. So if a degree is 3 and I have just one equation, then in 7 variables, the Hasse principle is okay. Actually, in a very neat form, there is always a solution, and the Hasse principle is trivially true. When the degree is 4, I need 12 variables to see that the Hasse principle is okay. But this time it's not of this style, that all equations in 12 or more variables will have solutions. There could be obstructions in the two-adic field. This is implicitly known by a paper of Bob Vaughan in 1989. And to just give you a feeling what happens when the degree grows, to establish the Hasse principle, at this moment, we need roughly d times logarithm d variables. This is certainly not sharp. I would expect that essentially, we will see this in a moment, d variables should be okay. D plus 1, d plus 3. All proofs of positive results that we have seen go through the circle method of Hardy and Littlebud. This was published first in 1922. So in some sense, the circle method has its 100th anniversary today. But it would be fair to include Ramanujan here. In a paper with Hardy, he had all the main ideas that gave the circle method later, and that was 3 years earlier. So how does the circle method work? It's a standard tool in analytic number theory, but it's often said the method is so complex that you would actually fail in any job interview to explain it in 5 minutes. I will not attempt to explain it in 5 minutes, but I want to give you the central flavor of the method. It's an idea that uses some elementary harmonic analysis. We work on the group R modulo Z, or if you like, just the interval from 0 to 1. And we map a real number alpha to the exponential function at 2 pi I alpha. So then the orthogonality relation, for Fourier series, if you like, says that if I multiply alpha with an integer n, then this knows whether n is 0 or 1. 0 or not 0, because if I put n equal to 0 here, then e at 0 is just 1, and the integral is obviously 1. And if n is non-zero, then it's easy to write down a primitive, and you see that the integral is 0. So now I want to use this relation to actually solve a single equation a1, x1 to the d, and so on, with s variables, equal to 0. Well, if the x's are just randomly chosen integers from a big box, side length 2p, it's just the maximum, all entries range from minus p to plus p. So when I have a bunch of numbers, this will be n, if I plug this in here, then this integral tells me whether I've hit 0 or not. So to make this precise, we introduce n of p that counts all the solutions of the equation I'm just interested in this box. And then we make the following observation. If n gets replaced by the green line here, then there are plus signs here. And the complex exponential cooperates with this and makes this a product. Well, if this makes this a product, and I'm summing over the x's in this box, then I can sum over each of the variables individually, and that motivates to introduce the function f of alpha, which is just the complex exponential at alpha x to the d, summed over this funny box, but now only in one dimension. And then we just see from the green relation that n of p becomes an integral, and now neatly this function f appears for each of the variables x exactly once. And so each of the functions f that appear here in this product takes the role of the xi's. So, of course, we haven't gained anything. The only thing that we see is that this function here that we have to plug into the integral neatly factorizes. And we can hope for some help if we understand the function f, at least whenever it's large. If it's small, then there won't be a big contribution to this integral. And that actually is the central idea of the circle method. If you evaluate the function f at a rational point a over q, and we think of q as being small compared with p, then you can see with the naked eye that the complex exponential, because it has period 1, will depend on x only in the residue class modulo q. So what I do is I just force x into a residue class modulo q and sum over all the potential residue classes. Then I can take the sum over b to the inside. Or we can think of this a little bit differently. The x sum that we see here can be very easily evaluated because I'm just counting how often is x in the correct residue class. So these points are spaced with distance q. So we're expecting something like 2p over q points for x. So there's a factor 2 missing here. That actually propagates through the slides. I just see this. And then the sum over b is still there, and that generates what people call a Gauss sum. That's this object S of q comma a. And if you like to have a little exercise, then try to see by the Chinese remainder theorem that this capital S here factorizes according to the prime factorization of q. That's important later. So now you see a big peak of this function f with a certain constant which is determined by the Gauss sum at rational points. And one can easily use Taylor's theorem or partial summation to get a little bit away from this a over q. And one sees from the error term that I wrote down here, but this error term still will be small if the shift from the rational number is no bigger than 1 over p to the degree, or maybe not much larger than this. So this suggests that f is roughly of size p, slightly corrected, as long as I stay away from the rational point at most like a small parameter x over p to the d. Well, then let's collect all these contributions from small q and small beta and call the resulting set the major arcs because they give a major contribution to the integral. If one collects that, what happens? Well, inserting this for all the f's, then I get a funny term chi infinity, I will say something about this momentarily, and a sum over the Gauss sums. And with chi infinity, if you want, I can go back a little bit, as products of such integrals integrated over beta. And what happens there is one actually sees the old equation again, this time over the real numbers, and with chi infinity as a kind of normalized measure for the surface of the equation that we are discussing. And I said before that these S functions here, the Gauss sums, factor according to the prime factorization. And actually, this here is a partial sum of something that is absolutely convergent. And because of this factorization property of the S, if you complete the sum over Q to infinity, you get an Euler product over all the primes. And this chi p that arises, again, is a measure of this surface, but no longer over the real numbers, now over the p-adic numbers qp. I've actually wrote down, for those who are interested, a down-to-earth definition of chi p just in terms of congruences. So now, let us suppose we are in a good situation, and this is when everyone is happy in applying the circle method, that this integral over these funny major arcs is the main contribution to the integral that gives me n of p. If that is true, then from 2 we can read off that n of p divided by p to the s minus d converges to this product that we have seen in 2. So now it is relatively easy to see, but one has to understand these surface measures a little bit better. But for an expert, that is something like standard. If S is bigger than the degree plus 3 or even 2, then you can actually say that the solubility of the equation in QP is equivalent to saying that chi p is positive. And likewise, with chi infinity sees whether we see, here's the equation, whether we see a definite equation when d is even. Otherwise, when d is odd, with chi infinity is always positive. So if this formula number 3 is true, and S is large enough, then this formula proves the Hasse principle. In this sense, whenever you have this formula 3, you have something more than the Hasse principle. You also know how many solutions there are. And one shouldn't be so surprised that S has to be taken bigger than D, because otherwise n of p would not even be large. So now, is this any good? Because I've done only those things that don't give you any meat. The complementary part needs to be estimated. And that is typically the difficult part of a circle method proof. So now, how realistic is this? There is a rule of thumb that these functions f decay with a denominator of q, roughly like q to the 1 over d, but the function f also generates some white noise. And that is square root cancellation on the length. So maybe this p to the 1/2 is a little bit over-optimistic. Maybe this is p to the 1/2 plus a bit. But if this white noise is here, then we cannot hope to prove anything better for the complementary set when we have s factors, p to the s halves. So if you now check these s halves against s minus d, you see that you have to have s bigger than 2d. Otherwise, the circle method typically doesn't work. And we call this threshold the square root cancellation barrier. One can break this square root cancellation barrier in ideal situations, but when you're not allowed to have modulus signs here, And that takes you into a very complicated theory where I won't say anything today. But I stretch out my neck, even though we have the square root cancellation barrier, I expect that for a single equation, the Hasse principle holds as soon as S is at least as large as d plus 3 or even d plus 2. We can't expect to do better than d plus 2. Remember, when d is 3, this says S is greater or equal to 5 is a conjecture that the Hasse principle holds. For 4 variables, it was false. So I'm happier with this conjecture. And more precisely, not only the Hasse principle is true, also its analytic description should be okay. And of course, this approach generalizes to our equations immediately. So in our equations, I wrote them down for you again counting in a box. So when I again see this functions f s times, but since I have r equations to take, for each of the equations I need one integration over r modulo z. And in here, you now see linear forms formed with the columns of a coefficient matrix. And the same philosophy runs now. We can work out the contribution that comes from small neighborhoods to rational points with the same denominator. The width is still the same, but remember now we have r such conditions. So the size of this box is now 1 over p to the r times d in volume, and therefore the size of n of p should be p to the s minus r times d. And then we see a similar product. And we remember this with this dagger here. That would be the prediction. So now a few remarks. Even if this is true, it's helpful only under certain conditions. We should have S to be bigger than what is subtracted for n of p to be large from this. If it is true, it confirms the Hasse principle. And therefore, we should have something like S is bigger than r times d plus a constant, whatever that is. And the square root cancellation barrier now reduces to S is bigger than 2 times r times d. You should remember this, because that is the threshold for the circle method to perform. 2 times the number of equations times the degree. So again, the question, is it realistic that we can prove a result with dagger down to the square root cancellation barrier? Well, I'm asking for too much, and I show you a new phenomenon. We look at a particular equation of degree 3, and this time I take a system that involves 2 such equations. Non-zero coefficients aj, many of them, s can be large, and I write down one equation, and I write down an equation that you have already seen, that is the Swinnerton-Dyer and Guy example, that violates the Hasse principle for one equation. And I can take the two together to form an equation of the type we would like to look at. So now, are there any solutions? And if so, how many? Well, the Swinnerton-Dyer-Guy example tells me the Hasse principle is false because there are solutions in all p-adic fields, in the reals anyway, but there is no integer solution other than the trivial one. So the second equation implies that the variables x1 up to x4 all have to be 0, and all this front block therefore disappears from the system. It only leaves me with a single equation in cubes, and there are s minus 4 variables left. So remember, when we have 7 variables, and that means that s is at least as large as 11, then n of p over p to the 7 tends to a positive limit by the result of Baker. Because, as I mentioned there, it doesn't actually matter, these coefficients only have to be non-zero. If I have 7 of these guys, then I already get a positive limit. But I have to divide this by p to the 3, and I lose these 4. So I'm dividing the original counting for n of p by p to the 7. But in Dagger, I was expecting that n of p over p to the 6 tends to a limit, which it certainly does not. So without a rank condition on the coefficient matrix, we can never expect that Dagger actually holds. So what goes on here? So there are solutions, but we struggle with the lower equation. It behaves in an irregular way. So what we need to know if we want to have that Dagger is true is that a single equation has enough variables so that it behaves regularly. So this suggests the following definition. You give me a number nu. In this system 1 here, nu is always 1. And I look at the coefficient matrix, and I'm trying to generate a block that only has zeros by row operations. And these should be zeros, as many as I can, in nu of the lines. So I make that maximal, and something has to remain here, when this block here still has rank nu. And the size that I reach here, if I make that maximal, is called q nu. So I can say this differently. Row rank is equal to column rank. So if you just look at the columns, then in this first block here, all these vectors lie in an R minus nu dimensional space. So I make that maximal, and what remains down here, that's defined q nu. So what we need is that this q nu here is big enough such that systems of degree d with nu equations and S nu variables behave okay, whatever that means. But that is a natural rank hypothesis, otherwise I cannot expect to prove anything. Okay. So here is the conjecture. Given a degree and a format S times R, and assume that the natural rank condition is of the following type: Q nu is nu times D plus 3 or something similar. It's not so important for now. And this has to be true for all the interesting values of nu. So note that when nu is equal to R, when QR is just S, this is why there's no condition on S in here. It's just coded here with nu equal to R. And then N of P should behave as we expect it to happen. So now let me show you two theorems that support the conjecture. So this is an old result that I proved with Travers-Boulet in the early 2000s. It took a long time to appear. So we just look at cubic equations, and we just take two of them, as in the example that I was discussing. So now if a number of variables exceeds 12, so I can compute, this is s bigger than 13, greater or equal to 13. But 12 is 2 times r times the degree here. So that's the square root cancellation barrier. Then the Hasse principle is true for all such equations. And if Q1 is at least 7, I need this from the Baker result, then NP essentially behaves like Dagger predicts. I don't get asymptotic equality, but I get a lower bound that is compatible with what we're expecting, because now R times D is 6. And then N of P is big. So this funny example where I was big when I divided out P to the 7 goes away in this. And here's another result that supports this. when R is arbitrary. Again, S should just exceed the square root cancellation barrier, which is now 6 times R, because D is free. And then we get the same result as we had in 2007, so essentially 10 years later. But this time, unfortunately, not for all systems. Only for those systems where a complicated condition on the ranks of the aij's is satisfied. Well, in particular for these systems, now the Hasse principle is valid. I don't want to go into the details what complicated means here, but let me give you a class where complicated is that is included in complicated, so that you get a feeling of what goes on. So you have now a huge matrix, format S times R, and you look for a quadratic submatrix. And if I know that all the quadratic submatrices are non-singular, so have non-zero determinant, then the complicated rank condition is definitely satisfied. So this means that all the entries have to be non-zero, all the 2 by 2 submatrices have to have a non-zero determinant, and so on. So, but in particular, if I randomly pick a matrix, then this should be okay with probability 1, because randomly you never choose 0 for a coefficient. Randomly you never make 2 vectors linearly dependent. That happens only rarely. So for a matrix in general position, the Hasse principle is true down to the square root cancellation barrier. So here's another phenomenon. Disjoint equations. So let me take R equal 2 for illustrational purposes again. And we have S as the sum of S1 and S2. This is again a hint that the rank condition cannot be avoided. If I want to check the Hasse principle for such a disjoint system where the variables only occur in one of the equations, actually one needs to check both of the equations to actually establish the Hasse principle, because it could be that up here I have an example where the Hasse principle fails, maybe, then there won't be any solutions here. But then in order to know whether this has solutions, even if the Hasse principle is true, then here I can only check this if I know it. So the Hasse principle for this system will only be true if it's okay for both of the equations. So that gives extra support to the idea that a rank condition is needed. And it generalizes to our disjoint equations immediately. I have to know it for all of them. So corollary, if we only know the Hasse principle from some point on for one equation of degree d, then for our equations, we will never be able to do better than linear growth in R. Let me go back to this because it slightly contradicts, apparently, to the Bruedern-Woolley theorem here, d equals 3, R equals 2. So if I have only 13 variables and I have a disjoint system, when one has 6 and one has 7 variables maybe, and then I don't know whether the equation in 6 variables satisfies the Hasse principle. But we are lucky, the equation in 7 variables always has a non-trivial solution. So if I find a solution, the Hasse principle is true. So that was sheer luck. So let's check whether S bigger than R times S1 is realistic. And you may recall that the Fourier result for S1 of D, currently we may take D times log D. And I proved long ago with Roger Cook over many beers that when NP behaves correctly, given that the natural rank condition is satisfied. So that's really what we were expecting. And you can now see how much we actually improved classical results when I worked with Trevor on d equal to 3, because you should remember that S1 of 3 was 7 by the Baker result. So we would only have something like r times 7 classically, and now we have r times 6 by the new results. I would like to show you an idea that is behind the Bruedern-Cook result. So let us assume that S is exactly r times SD. And now we're using linear algebra and some combinatorics. If a rank condition is satisfied, then one can say that after renumbering the linear forms, and that means renumber the columns of the coefficient matrix, then the first are linear forms and the second are linear forms and so on, all form linear independent families. So we have linear forms in R variables. So you can think of your original matrix falls into quadratic blocks R by R each, and each of these blocks is actually non-singular. So, and then I do some very simple analysis. I look at this product of the S functions and group these S functions into blocks of R. And then I apply a well-known analytic inequality. So then, so in this thing here, we have S functions F. In this block, we still have S functions F, but only F at lambda 1 up to F at lambda R. And I multiply this with S1. Remember, that's still S. And then the second block is being used and so on. Well, the lambdas are all linearly independent in each of these blocks. So I can just integrate this over the remaining set. So then I can integrate the right-hand side and change variables to lambda 1 up to lambda r. But when this r-dimensional integral factorizes to an half power, and now you can see if the circle method performed well with one equation, it will perform also with r equations, and it will have the same strength. And the rank condition only went into this elementary inequality. So morally, what goes on here, we are reducing the analytic treatment to the analytic treatment of a single equation. But everything happens somehow on the dual side. It's Fourier transforms. And for me, the Fourier transform also is some linear algebra. I've been cheating a little bit. This set here doesn't factorize. So one needs to work a little bit to make that work. So is there any hope to go beyond decoupling? Can we take advantage of entangled equations and then prove the Hasse principle for equations beyond what is possible by this decoupling idea that I just showed you? The answer is yes, and let me illustrate ideas in the case r equal to 2. It's clear how to generalize this, but it looks rather complex. So suppose now that I'm not just working with two linearly independent forms. Remember here, what we've been doing is we had many forms, we formed blocks, and then here, out of a sudden, we only have as many forms working as the dimension of the integration. So I'm just breaking that principle and say I have more of these as I see that here. So to make things simple, I denote the variables now with alpha and beta. I have two linear forms. One is alpha, the other is beta. And lambda 3 is just alpha plus beta. So then any two of these are linearly independent. And I'm interested in an object that has implicitly 3t functions f. So I have an exponent t here. Let us call this integral I. Well, you can play the decoupling idea so that we actually see what we have to debate. Then this reduces I to a moment of f with exponent 3t halves. But one can proceed entirely differently. We can even assume that this exponent t is not necessarily an integer. Not even, typically one would use only twice an integer. No, if t is greater or equal to 2, on the left-hand side, we have a differentiable function. So even if t is some strange number, so then it's represented by an absolutely convergent Fourier series with coefficients psi t. And if I apply orthogonality and note that the modulus of f to the t is an even function, I see that I is just the third moment of a Fourier coefficient psi t. And one can easily see for later that if we would work with free integrals, then a fourth moment would occur here. So somehow, if you this free here remembers the blocks, but the number of equations is just 3 minus 1. So now there are two methods to estimate this. Maybe actually 3 methods. Method 0 would be the famous inequality of Hausdorff and Young from harmonic analysis. That is nothing else than an abstract version of the green line here, that gives you that thing. And that's boring. But we want to build. Well, analytic number theory and harmonic analysis provide tools to show that for Fourier coefficients of a type we are considering, not in general, for these Fourier coefficients, large values of psi t are very rare. Well, then maybe we can just allow that these large guys, if they're being summed only over very few n, the contribution to I should not be big. And if psi of n is small, then maybe I can use an upper bound for psi t and reduce this to the quadratic moment, for which I have Bessel's inequality. So that gives me good estimates for I in some cases. There's also a different method which I want to show, and I call that complification. It's almost my last slide. So, and for this, it might be advantageous to look at exponents t1, t2, and t3. So then I can again use orthogonality and get a correlation of these 3 Fourier coefficients that we have already defined. So now we have a chance to apply Hölder's inequality to these 3, to this triple product, and I wrote down the result down here. So I get moments of these psi's with certain weights up here, and they have to sum to 1, as usual. So one possibility is to choose all these r's as 3. Then we're back to where we were before. But we are not forced to do this. And what now happens is, so if t is twice an integer, so even integer, and L also is a natural number, then what I said before, these moments here count solutions of a linear system in Dave powers. This is where we started. But now the format parameters are L minus 1, so that's the number of equations. And the number of variables in this game is 2t dash, so that's the t. So, but now we are allowed to have t and L, any positive real numbers. So as soon as we apply a step like this, subject to this relation, we are free to choose the choices for t1, t2, t3, and VL by choosing R1 and R2. So what we can do is, we can relate a pair of equations in a certain number of variables to linear systems in Dave powers and change the size parameters of this. And it's even possible to talk of something like 7.5 equations in 4 pi variables. Of course, now this allows for a very complex interplay between all these dimension parameters. And sometimes you have good estimates, and others you don't understand, and you apply the method 1, the large values estimates to this. So that looks like a very rich theory that should give something or nothing. Unfortunately, it gives something. For now, only for quartic equations, and this is still fairly fresh. Part 1 of this theorem is on the archive if you're interested. And for simplicity, I only look at quartic equations. And again, I only take 2 equations. And the result is when S is at least 22, and Q1 is 12. Remember, it was this one result, we need 12 variables for a single equation. Then N of P behaves correctly from below. And we have the Hasse principle asymptotically if I have 26 variables, assuming that, sorry, misprint, Q1 is at least 15. And that also is the current record for the asymptotic behavior of one quartic equation. Interestingly enough, even if S is down to 25, and again we have a complicated rank condition satisfied, then dagger still holds. So why is this breaking the general principle that I described? Well, if I need 12 variables to solve a single equation of degree 4, then by the standard methods that you've learned before, we have to double the number of variables. That would be 24, so we can do 2 variables better. And if we are looking at the distribution of the solutions and want that dagger is satisfied, so if D is 4 but R is 1, we need 15 variables. So we should have 30 variables for a pair in order to expect that. I'm a little bit unfair here because the condition on Q1 in number 2 should be Q0 is bigger than 14. So then the condition here should be that S is bigger than 28. But we still save 3 variables, or 4 variables even in 3, over the classical methods. So let me end by saying that we also have results with with 3 equations and more to come, although I don't really know what more here means. Thank you very much, and I'm happy to take your questions.
Thank you, Joerg, very much. A wonderful talk, wonderful talk. You get us all excited to study the circle methods. Well, let's see if there are comments.
Thanks, Michael.
Oh, comments congratulating you. It's a beautiful talk. Congratulations for this. Let me ask you one general thing. There are many students watching this, and if they are interested in the circle methods, where should they start?
Well, there is a Bible of the circle method, a book by Bob Vaughan, which is called The Hardy-Littlewood Method, Cambridge University Press. And there is a second textbook. So in some ways, of course, Hema, your career is related to Davenport, who was a close friend with Don Lewis. And and Davenport wrote a set of lecture notes in Ann Arbor in 1962. These are now available as a paperback book edited by Tim Browning, which is basically a one-to-one translation of the old notes into LaTeX. That is also that is a very nice read, and maybe a little bit easier to access than Vaughan's book. But Vaughan's book is more state-of-the-art than the Davenport notes, because they are from 62 and nothing has been done since to the text. But lots of things have happened in the circle method since.
Mm-hmm. But the Vaughan's book is 90s, 80s, or...
Well, there is a second edition from 97, and it has the smooth number stuff.
Okay. So maybe start with Davenport, then go to Vaughan.
Yes.
And then start, first your seatbelt and start reading Woolley, Bruedern, and all.
Or write me an email. That's also a possibility.
Woolley and you are, of course, I would say the big names on the Hardy-Littlewood method. And you start writing this result of Woolley of d log d, and I believe you're expecting to be linear, and I thought maybe you have put some effort on this, and you and Woolley, or not.
that would be a fantastic result if somebody manages to get dependence on the degree that is linear. So that would be a world-class result. Something I would love to do.
And you expect it to be true, isn't it?
Yes.
Yes, but with all this, there's so much technical obstructions in the middle that...
Yeah. So actually, I even, in a sense, I even formulated that as a conjecture. Let me see whether I find the right slide. Well, it's too early. So somewhere we must have conjecture on slide 10. So if people still can see the slides.
Just a minute. Now we can see.
Yeah, on page 10. So on top, that was exactly the conjecture. So one should be able to asymptotically evaluate this as soon as the number of variables exceeds r times the degree plus a constant. I'm not stretching out my neck for this 3, but.
You have for 3, you need 7, isn't it?
At the moment, I need 7, but so these conditions here are milder than what we actually know. Mm-hmm. So this is not really established in any case, other than obvious ones. So unfortunately, the conjecture is not really known, because even in the cubic case, I'm asking for more than what we know now.
Yes.
Yeah, r times d should be the answer, not 6 times r. 3 times r plus a bit. That was my claim. Mm. So I'm really believing that we should have linear growth in D. Linear in R we have, so Davenport and Lewis have started this, and they didn't get linear growth in R. So that is, linear growth in R was easy, somehow.
But this is also asymptotic value, so should work for large, very large D's, isn't it? For small D's, it's unpredictable in a sense. No?
Well, yeah, but my conjecture is concrete, So if you, I'm just saying that S needs to be bigger than R times D plus 3.
Okay.
Well, it's not an asymptotic conjecture, but...
Wow, yeah. Well, let's see if there are other comments. Oh, they are all congratulating you. It was a wonderful talk, And this is recorded. So
yeah, no problem.
No problem. So it'll be available if you want to see it again. There's there are all the papers of Bruedern. There are some in the archive, I believe.
Yes, one half of the final results is on the archive. The other half is not yet on the archive. Yeah.
Okay. So we have this references of the Davenport and Vaughan. We have all these slides. So we are all set to solve this conjecture now.
Exactly, and I would love to see it solved.
Okay, and I will do too. Okay, let's thank Professor Bruedern again for this excellent talk. We have now a break, and now I invite you all to go to the number theory section. At 11, we have a talk by Professor Mark Hindry. It's 11, yes, from Paris 7. Okay, so see you all at 11 in the number theory section. Bye-bye. Thank you all for coming.